So what we're looking at today is a similar topic to what we did yesterday with the approximation using, or linear approximation using the tangent line. Basically what we're going to be doing today is we're going to be finding the value, the approximate value, but we're skipping actually finding the equation of the tangent line and just finding the difference between the y-coordinate that we've got right now and the y-coordinate of the point that we want. That difference there is, we could say, delta y, the change in the y. We're going to approximate it using the differential dy, which you'll recognize from when we took derivatives, dy dx. Okay, so I want to run through some illustrations of this, and you try to stay with me through this because then we'll kind of wrap all this together nice and neat at the end, and it's actually a lot simpler than it may seem as we're going through it, okay? So let's, first of all, take a look at this situation here. So we've zoomed in really close on a part of this curve y equals x squared. And here's the point 1, 1 on that curve, okay? Well, then we have a line which actually is not showing up really well at all, but let me draw it in here. This line is like that. There's our tangent line, okay? There's our tangent line. And what we did yesterday is we would find the equation of that tangent line. In this case, it's y equals 2x minus 1. And then we plugged in the x value that we wanted. Okay, so we're trying to find this value, x squared. And we're approximating it by using the tangent line, so it's x 2x minus 1. Okay?
Wait, why shouldn't we use a closer tangent?
What?
Why don't we use a closer tangent?
Well, we haven't decided, we haven't stated yet what x is. We're going to see that down here. We're going to make sure we keep it close, because the further away from this value 1 that we get, the worse this is going to become. You know, you guys know the parabola continues like this, the line continues like that, so the difference is going to be much greater the further away from 1 we get. Okay? So what we're doing here is we want to find dy. Now dy we can do in this case because we actually can go ahead and plug in something and square it, and that's pretty easy to find. Okay, so the dy is the difference between the y value we have and the approximation. The delta y is the real thing. Okay? So we're letting y equals x squared. If x is 1 and dx is 0.01, all right, so what's the dx? Well, the dx is this difference from the 1 to this value right here, okay? So that dx, which is the same thing as delta x, is 0.01. So what are we actually finding here? We're actually trying to approximate the value when x is 1.01. Okay?
So dx is the difference between the point you have the tangent?
It's the point of tangency.
Okay.
And the point we're trying to approximate. It's the difference in x.
Oh, all right.
That is not questioned at all. That's why dx and delta x are going to be the same. We're finding a particular value for x. Okay? So that's 0.01. Now, if I were to do this using the tangent line, I would have 1.01, and I would plug in 1.01 into my 2x minus 1. So 2 times 1.01 minus 1, that's the point 1.01, 1.02 if you do the arithmetic there.
You're
Okay.
trying to find the point on the tangent line, right?
Yeah,
Yeah.
well, that's what we're finding here right now, okay? So what does dy equal here?
That's the height.
1.02.
Well,
just
the y
hold still.
coordinate, yeah, it's just the 0.02.
Yeah.
The difference, the dy is the difference between our approximation and the point that we knew. So we had it at 1, it has to go up 0.02. Okay, that's our dy. If I were to actually calculate what 1.01 squared is, which you guys can do that, it's just a little tedious. 1.01 times 1.01, we have 101, 2 placeholders because of the 0, and then another 101, 10201, and the decimals right there. Okay? So what is the actual delta y?
0.0201.
Yeah, 0.0201. So we're only 1/10,000th off in our approximation.
Wait, how do you?
Okay? The delta y is the actual distance we would have to travel to go from 1,1 up to 1.01 and its value.
How do you find that this one is the actual one?
This one we did because we knew the function was y equals x squared, and we just did the arithmetic. Okay?
Okay.
So this is one, all we're doing at this point is that we're seeing, as long as this delta x is not too big, our approximation using the tangent line is pretty close. Okay?
So delta x is the difference between the point you had and the point that you.
You want.
Okay.
Yes. Okay?
But if you were
Quick
not given
question.
delta dx, you can
Why
see
is the-
how it-
So here we have an illustration of kind of a bridge between what we did yesterday and what we want to do today. Okay? So yesterday we saw we had this point CF of C. Okay? And the equation that we had yesterday for the tangent line was this. Y equals f of c plus f prime of c times x minus c. And then once we had that equation, we could plug whatever we wanted in for x. So if we were doing the previous problem, we would do all this, then we'd plug in the 1.01. Okay, because that's the x value that we wanted. Alright? However, what we're finding here, if we wanted the change in y is going to be the y coordinate minus whatever f of c was. Right? That's this delta y.
Can you repeat?
Okay? The f of c, the y, is the point we're ending up at. And that, you can see over here, is this, we do c plus delta x, it's f of c plus delta x.
So that's why.
Okay? So the delta y is going to be this y value minus this y value. F of c plus delta x minus f of c. Just like you're getting slope. Okay? Back when we did derivatives for the first time. Okay? It's kind of like that. Okay? Now, this delta y, if we look at this diagram over here a little bit, you'll notice that f prime of c times delta x is this distance right here. Okay? That's that distance right there. That, from above, is what we called the dy. Okay, so notice we have a delta y. That's the whole distance from where we're at to the actual value. The dy is the distance from what we have to the approximated value. Okay?
The approximate value is.
The approximated value, yeah, it's on the tangent. So if we had drawn the tangent, here's that tangent line. Okay? So, the reason why this works is a little bit of right triangle trig, yeah. Remember, slope is tangent of the angle? Let me show you this here. This is dy. This is dx, which is the same thing as delta x, right? And let's say that this is the angle that your tangent line is making with a horizontal. Okay? Well, that angle right there is the inverse tangent of the slope. Okay? The slope is dy dx, and that's tangent of theta.
Okay.
That's the slope, okay? Well, what is the slope at of that line? It's the derivative at c. Okay? That's our slope.
Our slope is tangent of theta.
And the slope, well, don't worry so much about the tangent of theta, but that's why we're making it dy divided by dx. Okay? But the slope of the tangent line is f prime of c. Okay? And that's why we get, if I multiply both sides by a dx, we get dy equal to f prime of c times dx, or delta x. They're identical. Okay? That's why they labeled this little piece here f prime of c delta x. Okay? Now, where does the approximation come in? Here's where the approximation comes in. What we just found is the differential of y, dy. And you can see right here, it's what we just saw above there. dy equals f prime of x dx. Okay? At a specific point, it's going to be f prime of c dx. Alright? Now, remember, that is how far our approximation is from the original y. The actual value is this delta y, and this right here,
Wait, dy is how far is from the actual or from the point that you started with?
from the point we started with.
Okay.
Okay? The delta y, the actual difference in value, is approximately the f prime of x dx. So look, that's right, it's right up there. So as a result, delta y is going to approximately be dy. And that's where the approximation comes in. Okay? Now, there are some different properties here that apply. All these properties are directly from our derivative properties. Okay? If you have a constant in the differential of a constant multiple, you can pull the constant out. If you have a differential of two functions added together, you can take the differential of one plus the differential of the other. You have the product rule, you have the quotient rule. Works still with differentials, alright? I'm not going to spend a ton of time on those, but here's where all of this stuff we've been talking about kind of ties together, and it actually ends up being much simpler than we might think, alright? Stay with me for a sec.
Okay.
Okay? Here are our functions, here are our derivatives. Y equals x squared, dy dx is 2x. What would the differential of y equal then? dy.
dy
So
equals
dx
2
times
dx.
2x
dx.
times dx
2x
times dx.
times
dx.
dx. Yeah.
That's all we have to do?
If y is 2 sine, then dy dx is 2 cosine. So what does dy equal?
dy 2 cosine x dx.
2 cosine x dx. So check out all these. All we're doing is we're multiplying by the dx. Think about it as the derivative gives us the slope, and the dx gives us a fraction of the slope that we need to travel in order to get to the correct y value. Okay? Or to get to the correct point.
Oh.
So let's tie this back and do the same problem we did yesterday. We had that function f of x equals sine x plus 1.
Yeah.
And we were using the point f of pi over 6. Okay, and we got pi over 6, sine of pi over 6 is a half, plus 1 is 3/2. Okay? And then we said we wanted to approximate f of pi over 6 plus a 0.1. Okay? So notice here how this is kind of a streamlined version of what we did yesterday. We do not actually have to find the tangent line. What we're going to do here is we are going to find dy. Okay? dy is f prime of x times dx. Okay? So we need to identify some things here. What's f prime of x?
Cosine x.
Cosine x. What is dx? 0.1. Okay? So, what I'm going to do here is I'm going to actually take, and dy is going to be f prime of the pi over 6 times the delta x. Well, what's f prime of pi over 6? It's cosine of pi over 6, root 3 over 2. Okay? Cosine pi over 6. And then we're going to multiply this by a 0.1. So it's root 3 over 2.
But we still have a rational number.
Okay? Yeah, so it's root 3 over 20. If we simplify that. Now, that is not f of pi over 6 plus 0.1. That's the differential. So, that's our differential. F of pi over 6 plus 0.1 is going to be f of pi over 6. Or I should say equal. I should say approximately f of pi over 6 plus the dy. So, we knew that that was 3/2. And now we just found that dy is root 3 over 20. If we want a common denominator, we could make it 30 plus root 3 over 20. Okay? That is an approximation of the sine of pi over 6 plus 0.1. Let's look at one more example. We're going to approximate the square root of 16.5. Okay? So you've got to do make some inferences here. First of all, what's our f of x that we're dealing with?
X squared, x.
Square root of x. Yeah, square root of x. That's our function. So obviously, f prime of x, you guys know this, it's going to end up being 1 over 2 root x. Okay? Now, you've got to think, on the square root of x, what's the closest value of x to 16.5 that I know the square root of?
16.
I know 16, yeah. So I'm going to let c equal 16, and that means f of c is going to be 4. Okay? That also means my dx equals what?
0.5.
Yeah, the 0.5. How far away is the point I want from the point I know? It's 0.5 away. Okay? So, when I'm doing this, alright, what I want to do is I take the dy and that's going to equal, it's going to equal f prime of 16 times the dx, 0.5. Okay? F prime of 16 is 1 over 8. So 1/8 times 0.5. And that means dy is 1/16.
Wait, how do you know that f prime of 16 is equal to 1/8?
Just plug it in.
I plugged 16 into f prime of x.
Oh, right, never mind.
Yeah. You know that. Okay, so there's my dy. So guess what? The square root of 16.5 is going to be approximately the square root of 16 plus that dy.
So 4.
Why approximately?
Well, because this is on the tangent line. This is dy. And remember, dy is approximate, well, I should put equal. That's approximately what the delta y is.
Yeah.
The delta y is the actual, the dy is an approximation. Okay? So, this is going to be approximately 4 and 1/16. Okay? So now we have a pretty good approximation of what that is, and then we could use it moving forward. Now, we're 0.5 away. That's not going to be as good an approximation as we could get if we had 16.1 or 16.2 or something like that. Okay? And actually this brings us to the real difference between and the advantage or disadvantage of the two methods that we've learned yesterday and today. Okay? If I just want to find one value like this is faster. Okay? I've cut out the step where I actually had to find the whole equation, and I'm jumping right to, hey, what's the difference in value, add it to the original, and I've got it. Okay? Where the tangent line approximation is more helpful is, let's say I wanted to approximate also 16.1 and 15.8 and some other values. If I had the equation of the tangent line, I could simply plug those different x's in and get all of those approximations immediately. This method requires me to, I'd have to plug in different delta x's and then add them to the 4 every time. So it's a little bit faster if we had the whole equation to just be able to plug in the x value, if we had to do multiple. Just, yeah, to illustrate that, if I wanted to get the actual tangent line, I would use that slope I found, the 1/8, and I'd use this point of tangency that I have. So it would be y minus 16, or sorry, not 16, y minus 4 equals 1/8 times x minus 16. And I'd have y equals 1/8 x minus 2 plus the 4 would be a plus 2. If you plug in a 16.5, okay, y is going to be, I'm plugging in the 16.5 times 1/8, it'd be a plus 2. Alright, 16.5 divided by 8 is actually a 2 and 5/80ths, which is 2 and 1/16. Alright, so 2 and 1/16 plus 2, 4 and 1/16. I'm getting the same approximation.
Can we just do that?
If it just says to approximate, then yeah, you can pick whichever method you want.
Okay, it's
If it says to use differentials, then we should be seeing this. If it says to use a tangent line approximation, then I should see the equation of the tangent line somewhere.
Yeah.
Okay? So, just pay attention to the directions on the problem. If it says to use a particular method, please use the correct method.
It's
Okay.
just the answer is 4 and 1/6, not 2.
Oh, yeah, thanks. I hate when it does that. 4 and 1/16.
Yeah.
Can do the calculus, just not the arithmetic. Alright.